everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering the chi-square distribution, where it comes from, what it's shaped like, and how it lets you make statistical inferences about variance. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's wondering if his results have actually been getting more consistent lately, whether studying these letters has actually made his outcomes less variable. He opens up another one of those mysterious letters. You've seen that when you have a small sample, you can't just use the normal distribution for inference about the mean. You need to use the t-distribution because the sample standard deviation is uncertain. Now we're going to ask a related but different question. Instead of making inferences about the mean, we want to make inferences about the variance itself. To get there, let's start somewhere concrete. Suppose a meteorologist forecasts tomorrow's high temperature every day for a week. Each day there's a forecast error, forecast minus the actual, and those errors are approximately normally distributed with mean zero and some standard deviation. Now you want to measure how accurate the forecaster actually was for the whole week. The obvious first move would be to add up the errors, but here's the problem. Positive and negative errors are going to cancel much like they did when we were talking about how we created the variance formula. If the forecast was 5 degrees too high on Monday and 5 degrees too low on Tuesday, those mistakes disappear when you sum them up. The forecaster looks like he was perfect when he wasn't necessarily. So you could take the absolute value and sum those, and that works for the cancellation problem. But the reason we square instead of taking the absolute value is more interesting. Squaring each error before summing produces a total that follows a known, mathematically traceable distribution, called the chi-square. The absolute value of a normal variable gives you a much harder distribution to work with. Squaring is what connects measuring total error to having a distribution you can look up and use. And once you have a known distribution, you can start putting probabilities on things, asking whether a particular total squared error is surprisingly large or whether it's within the range of normal sampling variation. We'll formalize exactly how to use these probabilities as a testing framework when we get to inference, but the foundation is all right here. So we square Monday's error and add Tuesday's squared error all the way through Sunday's. That sum of 7 squared standard errors follows a chi-square distribution with 7 degrees of freedom. Written out, if you take k independent standard normal variables, call them z1 through zk, and square each one and then add them up, the resulting distribution, which we'll call q, follows a chi-square distribution with k degrees of freedom. 3 key properties exist for chi-square distributions. First, this distribution q is always greater than or equal to 0. It's a sum of squares, so it can never be negative. The second property, since we're assuming these variables are standard normal, is that the expected value of our chi-square distribution is going to be k, the number of observations, and the variance is going to be 2k. So the more degrees of freedom we have, the higher the mean. Third, this distribution is right skewed, especially for small k. It has a long right tail and is bounded at the left at 0. As k gets large, it approaches normality, the same pattern as the t-distribution. So why do we care about this distribution? Well, we commonly use it when we're dealing with things like variance. Think about what the sample variance s squared actually is. You take each observation, measure how far it sits from the sample mean, square that distance, and average them up. That's it. It's a mean squared deviation, which means it's doing exactly the same squaring and summing operation as the weather example, just applied to deviations from the mean rather than forecast errors. And just like in our weather forecasting example where things followed a chi-square distribution, the sample variance, once we scale it appropriately, is also going to follow a chi-square distribution. Specifically, if you take n minus 1 times s squared and divide by the true variance, sigma squared, that quantity follows a chi-square with n minus 1 degrees of freedom. The scaling is what makes it work. You're expressing the sample variance in units of the true variance, so the result is dimensionless and lands on a fixed known distribution, regardless of what the actual units are. That means if you have a reference value for sigma squared, you can compute this quantity from your data and immediately know where it sits on the chi-squared distribution. So now let's work through an example. A fund has an established monthly volatility of 3.46%, estimated for many years of history. You look at the most recent 25 months, and the sample standard deviation comes out to 4.5%. Is the recent period genuinely more volatile, or could that difference arise just from the fact that you're only sampling 25 months? To set up the statistic, n equals 25, s squared is 4.5% squared, which is 0.002025. What we're testing against is the historical level. the 3.46% squared, which is approximately 0.001197. The chi-square statistic is n minus 1 times s squared divided by sigma squared. That's the 25 observations minus 1 to get 24 degrees of freedom, times the 0.002025 for s squared, divided by 0.001197, which gives us approximately 40.6. A chi-square with 24 degrees of freedom has its mean at 24 and its 95th percentile at about 36.4. The statistic, 40.6, sits above that. If the fund's true volatility hadn't changed at all, a result this large would occur less than 5% of the time just from sampling 25 months of data. That's a useful benchmark. When we get to statistical inference, we'll build the formal decision framework around exactly this kind of tail area calculation. One thing worth noting about the chi-square shape, it's bounded at 0 and skewed right, so the critical region for a large observed variance sits in the right tail. A larger sample variance produces a larger chi-square statistic, so high values are evidence the true variance is elevated. For questions about whether the variance is lower than the reference level, you look at the left tail instead. And if you want to ask whether the variance differs in either direction, higher or lower, you check both tails and split your probability threshold between them. Danny puts down the letter. He's been keeping a gambling log for years, all the session outcomes and how every single one of his gambles ends up playing out. He has a long enough history that he has a solid sense of his baseline variance, how volatile his results usually are. But he feels like lately he's been getting a lot more consistent, and he wants to figure out if that's the case. Specifically, since he started listening to the advice in these mysterious letters about 28 of his gambling sessions ago, he's noticed that he's become a lot more consistent, and he wants to figure out if this consistency is just a random fluke or if it's something that he can actually trust. So he treats his long-run historical variance as the reference level and applies the chi-square framework to his recent sessions only. Here, n equals the 28 recent sessions since he found the box. He calculates the sample variance from those 28 sessions, and it comes out to about 38% below his historical baseline. He computes the chi-square statistic, 27 times the new sample variance, divided by the historical value. That gives 16.9. With 27 degrees of freedom, a value that low sits below the 5th percentile of the chi-square distribution. If nothing had actually changed, a result that low would come up less than 5% of the time, just from the natural variation within a 28-session stretch. It's borderline, but it clears. He's been getting smarter. The outcomes are becoming more consistent, not because he's been winning more, but because he's been making better decisions. And better decisions produce less randomness in the results. He can see it in the numbers now that listening to the rational quant's advice has been helping him. So that's the chi-square distribution. It arises as the sum of squared standard normal variables. It's always positive and right skewed, and it's the right tool whenever you're making inference about variance rather than the mean. The key statistic is n minus 1 times the sample variance divided by the reference variance. That quality follows a chi-square with n minus 1 degrees of freedom. When the statistic lands far in the right tail, the realized variance is higher than the reference level. When it lands in the left tail, the variance is lower. That ends up being foundational for volatility analysis, risk model validation, and is also directly related to the next distribution we're going to cover.